Welcome everybody to this channel. In this video I will explain the analysis and the actual construction of a replica Ulfbert sword based on an original sword from the museum. In this video I will explain a radical new hypothesis that states that technological development locally in Western Europe was available that can explain most of the high carbon steel found in these magnificent swords. The entire process will be replicated from making an historical bloomery, remelting the iron in remelting furnaces and actually forging the different billets into actual artifacts. The star of the show is an Ulfbert sword found in the river Waal near Nijmegen and can be dated roughly to the middle of the 10th century. This particular sword has the spelling plus ULFBERH+T, which is indicative of the high carbon steel swords. Furthermore, the woven lattice pattern on this sword is quite similar to other plus T category Ulfbert swords, making it likely that this particular blade belongs to the high carbon category as well. The sword was analyzed by means of a handheld XRF tool. This is a non-destructive analysis technique that can determine the chemical composition of the metal alloys in the steel. Unfortunately, the tool also has some limitations. In particular, lighter elements cannot be measured accurately, so carbon content, phosphorus content cannot be judged with the handheld XRF, but the metal alloys can be determined to quite high accuracy and quite low concentrations very accurately. The ratio of elements, chemical elements that can be found in this sword are of course interesting to see if we can match those to a particular mine or ore deposit from a specific region and see if a match in local trace elements can be found. Especially since the chemical composition of the steel shows quite specific markers that can perhaps be tied to a local ore or mine. In particular, the sword shows quite a high cobalt concentration, but also furthermore contains copper, zinc, molybdenum of 0.07%, nickel, manganese, arsenic, titanium, chromium, vanadium, a little bit of lead and a very small amount of barium. In particular, the cobalt concentration of 0.4%, copper content of 0.2%, a zinc ratio of 0.1% and a molybdenum concentration of 0.07% are quite interesting. Furthermore, we see trace concentrations of titanium, chromium and vanadium, which are also quite specific markers for a certain ore or region. We also investigated if the different areas of the sword, for instance the core or the edge steel, have a different chemical composition or can be traced back to different types of iron. That is not the case. The overall chemical fingerprint of all the different areas of the sword show a quite similar response, hinting that they all originate from the same mine, but with some very interesting nuances. The core area of the sword, the inner area of the sword, shows an elevated arsenic concentration, while the edge steel and also the outer surface, the outer layer of the sword doesn't show any response in arsenic. This makes us to believe that the core area is made of a bloomery type of iron, while the edge steel and the outer surface panels are more refined by a steel making technology. The inlay material, on the other hand, does show a different chemical composition compared to the bulk of the sword. In particular, it shows a very high arsenic trace that is indicative of high phosphorus bog iron. High phosphorus types of iron will usually give a nice bright contrast compared to a purified type of steel in the final blade, and particularly when it is smoothed by grinding or polishing to a high luster, it will stand out from the main body of the sword. This is in line with some of the other analysis done by other scholars on Ulfbert type of swords. Although the overall appearance of the blade is still quite good, especially considering it has been laying on the riverbed for almost 1,000 years, in certain areas the sword is also quite corroded. And this gives us a rare opportunity to actually look inside of the sword to see how this particular blade was constructed. It seems that the sword was built from 5 individual main bars. One core billet, which was then flanked by 2 bars of edge steel, which is then fully encased by 2 cover panels. And because these cover panels reach all the way to the extremity of the cutting edge, it gives the appearance that the entire sword is made of a monosteel, but in fact this is certainly not the case. I will go over the individual bars and give a brief description how at least I think they were made based on the chemical analysis and the visual appearance of the different bars. Let's start with the core billet. Based on slight color nuances that can be seen in the different layers of the core billet, it seems that the core of the sword was made of a laminate material. Looking into the XRF chemical responses, it hints that 2 types of iron and steel were used. Most likely one of them is primary bloomery material and the other one is a refined steel, which are both forge welded together and then folded and welded back on itself around 4 times. This gives the layer appearance that we see in the blade, and that means that the core interior is made of a composite laminate material of iron and steel, made in very thin layers. Combining iron and steel into a laminate sword interior makes that the sword becomes practically unbreakable, while still having the benefit of a hardenable core by the thin steel layers. Although that the edge steel also has a layered appearance, there is no indication that 2 types of iron or steel were used, but it has more the appearance that the same bar of steel was refined by folding and welding it back on itself several times. Also, the chemical analysis of different spots over the sword of the edge steel show that they are very uniform in composition. Normally edge steel needs to be folded and welded at least 6 times back on itself to become of sufficient quality for edge steel, and it seems that this layer count is more or less also available in this particular sword. In contrast to the core billet and the edge steel, the outer surface panels do not show any signs of being refined by the fold and weld technique. And this is very unusual because steel in medieval times normally needs to be folded and welded back on itself in order to purify and homogenize the iron enough to be serviceable as a steel in a sword. It is therefore proposed that the cover plates are made of a fully liquefied hearth refined steel. This is quite a controversial topic, so further supportive evidence of this theory will be presented in this video. It must be noted that Both the edge steel and the cover panels show a very similar chemical composition or chemical makeup, and are therefore assumed to be both of the half refined type of steel, with the big difference that the edge steel was refined by a fold and weld process, while for the cover plates it seems that the ingots were just hammered out flat and cut hot cut to match the sword blank. So now we know how this sword was constructed. Let's see if we can find a local provenance for the raw materials that were used in this sword, by starting with the area where the sword was found and extending basically the search area bigger and bigger until a match in trace elements can be found. The area where the sword was found in the Netherlands historically was called the Hameland and encompasses roughly the central area of the Netherlands, covering both the Veluwe and the Montfertland region. In Viking times, iron was produced in the Hameland region on a mind-boggling scale. We know from slag heaps and open pit mines that in the Veluwe area more than 55 million kilograms of steel must have been produced in the early Viking times. And slightly later Viking period or middle Viking period, a little bit further to the east, 6 million kilograms of iron and steel must have been produced in the 9th through the 11th century in what is now the Montfertland region, making the Netherlands the largest iron production site of Western Europe in the Viking Age. The reason for this enormous amount of iron production in the Viking period is that a very unique and pure type of iron ore can be found locally in the Netherlands. This iron ore is called rattlestone because it makes a bit of a rattling sound when shaken, and is formed in conjunction with glacial depositions during the last ice ages. Because of the unique way that this iron ore was formed, which is quite unique and different from other types of iron ore, it makes this iron ore very pure, but also bears very specific trace elements due to the way it was formed. Chemical analysis have shown that the iron ore can contain as much as 90% iron-bearing minerals, and usually has some specific trace elements, particularly aluminum or alumina, because it is formed around a loam core, and also has 3.5% manganese oxides present in the ore. But just as importantly as the elements that are present in this ore are also the elements that are not there. Particularly phosphorus and sulfur are hardly present in this type of ore, making it a very valuable and unique type of iron ore. Furthermore, the trace elements found in this type of iron ore match perfectly with the chemical analysis of our sword under investigation. We find cobalt, copper, zinc, nickel, arsenic, but also titanium, chromium and vanadium, and small amounts of molybdenum in this ore as well, giving it a 100% match in the trace elements of the Ulfbert sword. But just as importantly, other specific elements that are not found in these ore are also not found in the Ulfbert swords, giving a double confirmation that the type of iron ore was very likely used for the production of the Ulfbert swords. The unique combination of a 3.5% manganese with high content of iron and a very low phosphorus contamination makes that the iron produced from rattlestones is very prone to carbon absorption, as can be seen from this particular bar, which is made from rattlestone bloomery iron. The carbon affinity of this iron made from rattlestones is probably the core reason for the millions and millions of kilograms of steel produced in the Viking Age. In contrast, iron produced from bog ore, as many other countries had to rely on, is very difficult to turn into a steel, as the phosphorus will inhibit carbon migration and will actually push out a little bit the carbon once it is there in the steel, making it very hard to use as a source for swords. In contrast, iron made from rattlestones will already absorb enough carbon during the refinement stage of folding and welding to be considered a hardenable steel, although low to medium carbon levels. Although more analysis is needed, some initial findings may support that this primary bloomery steel was used in the uh, other category Ulfberts, which are more spelled like plus Ulfbert and the cross at the end. Analysis done by other scholars on this category swords show a very identical chemical composition as the sword that we have analyzed for this article, although they are usually made of a low to medium carbon steel, and there is some indication that refinement has taken place in the form of folding and welding, indicating that both category swords are made from rattlestone iron ore, but that only the Ulfbert swords, which have a cross and a T at the end, are made via a secondary hearth refinement technique. Also, other inscribed swords of the same Viking Age show a very similar chemical composition as the Ulfbert swords and are therefore most likely made from the same type of rattlestone iron ore. For instance, this is the beautiful Ulfberht sword, which is also housed in musea in the Netherlands. Not only is the chemical composition very comparable between swords, but also the markings at the back are very similar, if not 100% identical, between Ulfbert swords and the Ulfbert sword, giving credibility that this was a local type of manufacturing technology that produced the inscribed swords. As a side note on this particular topic, also Inglery swords show an exactly identical woven lattice pattern as on some of the Ulfbert swords, grouping the name inscribed swords as a group to a specific region, or more specifically to the Hamaland region of the Netherlands in the Viking Age. Inglery swords have not been chemically analyzed as far as I am aware of, but I am pretty sure they will match the chemical composition of the Ulfbert swords, also to the use of rattlestone iron ore. So let's also see if we can find evidence of local high carbon steel technology in the Netherlands. And luckily there is. At the iron production site at Heaton, already in the late Roman era, hypereutectoid high carbon steel artifacts were being produced, as is evident from the famous Heaton artifact, which shows a 2% carbon content and furthermore was already heat treated and back tempered, showing that high carbon steel technology was already available in the Netherlands from quite early periods onwards. Furthermore, fully liquefied ingots have been found in slag heaps that match the chemical composition of rattlestone iron ore, and therefore can be dated also based on the slag heaps of the same area that have been dated broadly to the Viking Age. What is remarkable is that these fully liquefied ingots show traces of two types of slag adhering to them. One is the black typical Phaeolithic bloomery type of slag, and the other one is more a whitish type of slag, which resembles more a flux that was used during the production of these ingots. From the same slag deposit as the fully liquefied ingots were found, also clay blocks have been retrieved that can best be identified as parts of remelting furnaces. These are most likely little doors that were cut out of the clay furnace when the clay was still wet to aid in the extraction of the ingots when the smelt was over. A highly glazed surface coating of these clay blocks show that they have been subjected to extreme heat, but the glaze looks more like a ash type of pottery glaze and not so much a bloomery slag type of glaze. This, in combination with the two types of slag that we see on the actual steel ingots, allows for the possibility that wood ash was used as a flux during the liquefaction process of these ingots. Hardwood ash is primarily comprised of calcium and potassium rich oxides and are therefore considered highly alkaline. Alkaline rich slags, particularly high in calcium and potassium for that matter, have the ability to absorb phosphorus in the form of calcium phosphate out of the iron and bind it to the slag. This will highly purify the iron in this case. But more evidence is available that remelting of bloomery iron took place. At the site of Dale and Gloenen, multiple iron working furnaces have been retrieved in an archaeological context dated to the Viking Age that in my opinion can best be explained as remelting hearths or finery hearths. To test whether steel can be made with Viking Age technology that is similar to the quality of steel we see in the Ulfbert swords, the entire process from making primitive bloomery iron from rattlestones to remelting in dedicated remelting hearths and to forging the produced steel into bars and knives was fully tested. Not only is the knife of very high sharpness, but in particularly what stands out is the edge retention, hardly dulling during everyday use in the kitchen. Vastly outperforming modern factory-made blades from the famous Solingen brands, particularly on edge retention in daily use in the kitchen. Next to a knife that was produced in order to test the heat treatment techniques for this particular half refined steel, the beginning of a sword is also made. Here we see the core bar of bloomery iron mixed 50% with half refined steel, which is further folded and welded 4 times, around which a edge steel of fully liquefied half refined steel is forge welded already. On the left we see the cover panel, which will subsequently be forge welded around the core bar and the edge steel. This is the way the Ulfbert swords were made historically. Here we see the entire billet ready to be forge welded into a single bar. Note how the edge steel is slightly protruding out of the middle of the billet, but is fully encased by the cover plates. Here we see the entire billet being forge welded into one complete homogeneous bar. It actually makes a lot of sense to construct the entire sword or sword blank out of multiple smaller bars, because individual smaller bars are much easier to refine with the right amount of heat and expel the slag content out of multiple thinner bars is much easier done than when considering one big full chunk of steel. Also, when constructing the sword blank from multiple smaller bars, this allows for the core billet or the interior of the sword to be made of low to medium carbon pattern welded steel. So when the fuller is then forged into the middle section of the blade, meaning that we make the middle part of the sword thinner, when the blade is subsequently quenched, the low to medium carbon core of the sword will cool fast enough, because it is made thin, to also harden. And just as importantly, it will also allow for a back temper or a spring temper to be drawn on the blade with additional heat treatment. Early medieval steels, in particular low to medium carbon steel, need quite fast cooling rates in order to properly harden, and making the middle portion of the blade thin is the solution to this particular problem. Therefore, applying a fuller in a sword is a marvelous innovation of the early medieval smith, and shows the know-how to effectively incorporate different types of steel into sword design, but also show that knowledge of tempering and advanced heat treatment techniques were known. Actually, applying a fuller into a sword design only makes real sense if carbon steels have been applied into the body of the blade. With remelting of bloomery iron via the hearth refinement technique, providing the best quality of high carbon steel. All the iron that was produced for this study was analyzed by means of the handheld XRF, micro XRF, or wavelength dependent XRF, and compared against the chemical analysis of the Ulfbert sword. So by comparing Rattlestone bloomery iron against half refined iron of the same starting material, quite some interesting traits were identified. First of all, slag can be expelled from the bloomery iron quite efficiently via the hearth refinement technique. Furthermore, plain iron can be upgraded into a high carbon steel quite effectively by the hearth refinement technique. It is also found and measured chemically that arsenic will evaporate out of the iron matrix due to the high temperatures during the hearth refinement, as the melting point of arsenic metal is actually quite low. On top of this, if wood ash was used as a flux during the hearth refinement technique, the calcium content of the hardwood ash has the ability to absorb phosphorus out of the liquid steel into a calcium phosphate rich slag, purifying the metal considerably. It is even found that due to the high amounts of charcoal ash that are used during the hearth refinement technique, the slag inside of the steel will have an elevated calcium and potassium content, in particular with a ratio of about 2 to 1 calcium to potassium, or in a broad sense between 4 to 1 to 1 to 1, as is normal with hardwood ash like oak or beech. Some of the Ulfbert swords, particularly with the +T category, have been analyzed to have a slag content with 16% calcium in its slag, and furthermore have a 2 to 1 calcium to potassium ratio. It is therefore also found in the actual Ulfbert swords that the mass balance for calcium, potassium, but also for manganese fits with hearth refinement. By looking at the slag composition inside of the steel of actual Ulfbert swords. Lastly, it was found that, and particularly when the hearth refinement furnace was run extremely hot, and where quite a lot of bloomery slag was part of the remelted iron, that Manganese from the slag could be reduced out of the slag into a metal alloy proper. But also nickel and cobalt seems to be concentrated out of the slag into its metal form, forming a iron metal alloy. Also, these findings are comparable to actual Ulfberht swords, and in particular the sword found in the river Weser in Germany, which had a 1.5% manganese metal in the actual sword. And in the hearth refinement experiments with rattlestone iron, also a 1% manganese alloy was formed that could also be measured by means of XRF. To summarize on the hearth refinement technique, all the mythological qualities that have been attributed to Ulfbert swords can be explained by the hearth refinement technique. First of all, it is quite easy to create hyperotactoid steel via the hearth refinement technique, in particularly suitable for rattlestone bloomery iron. Next, slag will be expelled out of the bloomery iron because the metal is made almost liquid, and the calcium-rich hardwood ash slag bath will absorb some of the phosphorus out of the steel matrix into the slag. But also manganese will be or can be reduced out of the slag into a metal alloy proper, vastly improving the characteristics of the steel altogether. Lastly, the metals chromium, vanadium and titanium have been measured in the half refined steel, the experimentally produced half refined steel, most likely in the form of metal carbides, creating tremendous hard spots in the steel's matrix. The knife that was produced from the half refined steel made from rattlestone bloomery iron was also analyzed by means of the handheld XRF and compared against the chemical trace elements of the actual Ulfbert sword under investigation. The similarity by the two types of steel is astonishing. Both show basically identical level of cobalt, nickel, manganese, chromium, titanium and vanadium. Basically the only element that differs between the knife and the Ulfbert sword is the zinc content, where the Ulfbert sword has a 0.1% zinc and the knife almost 10 times lower concentration of zinc. This can be explained by the local origin of the rattlestones that has been used for the creation of the knife. The rattlestones for the knife originate from the Veluwe region, which is known for its low zinc content, while the rattlestones from the Montfertland region are known to have a much higher zinc content naturally present in the ore from the Montfertland region. Pinpointing the provenance of the Ulfbert swords almost to an exact local mine in the Montfertland region. And last but not least, known iron production in the Montfertland region matches perfectly with the known dates the Ulfbert swords were produced. Both are dated to the 9th to the 11th century. Now I guess this is enough for today. I hope you have enjoyed watching this video as much as I have creating it, because what a journey it was. Investigating hands-on actual Ulfbert swords, creating with friends bloomery iron, which is further consolidated and purified with the hearth refinement technique, but also running the analysis has been a lot of fun. If people are further interested into more Ulfbert content, just leave a comment below, and please also share this video so it will be distributed to a broader audience. If people like, I can also make videos on historical Viking Age forging techniques, for instance, Viking Age forge welding, or I can also explain a little bit more about the historical and the sociological context in which these swords were created. But I can also tell a little bit more about the Ulfbert swords, Ingolri swords, Giselin swords, and where I think they were most likely being produced exactly.